Hello, everyone. Thank you for joining us for today's Koringo Tech Tuesday webinar. This session's topic is S3 Storage Secrets, What Vendors Aren't Telling You. I'm John Bell, Senior Consultant at Caringo. Today I have as our guest, Koringo Director of Product, Eric Day. Eric and I will be available to answer your questions throughout the webinar and at the end of today's presentation. In addition, we have a couple of resources available by the Attachments and Links window on your view screen. If you have any questions after the webinar, you can always reach us by email at info@koringo.com. Just some quick introductions before we dive into things. Again, I'm John Bell at Caringo. I've been with Caringo for over 7 years, and I'm a senior consultant based in Austin, Texas. I specialize in the design, implementation, and management of object storage. I've worked with many of our largest customers to transform their storage infrastructure with highly efficient and cost-effective object storage solutions. Eric, please introduce yourself.
Thanks, John. As you know, I'm one of the early developers of the Swarm object storage product, and I've held a number of positions over the years at Caringo. I come from an IT background, and essentially I've been building the storage product that I've always wanted in terms of ease of day-to-day management and year-to-year scaling and evolution of the hardware underneath it.
Excellent. Thank you very much, Eric. Just a quick word about us at Caringo before we dive in. Caringo was founded in 2005 to change the economics of storage by designing software from the ground up to solve issues associated with relentless data growth. Caringo's flagship product, Swarm, decouples data from applications and hardware, providing a foundation for continued data access and analysis that constantly evolves while guaranteeing data integrity. Today, Caringo software-defined object storage solutions are used to preserve and provide access to rapidly scaling data sets across many industries by organizations such as NEP, Argonne National Labs, UK Science and Technology Facilities Council's Scientific Computing Department, Texas Tech University, US Department of Defense, the Brazilian Federal Court System, British Telecom, and hundreds more worldwide. So the rundown for our agenda today, briefly we'll dive into what is S3 as a storage protocol. What are some of the things that you might be missing when you're evaluating S3 solutions and trying to determine, what's best for you? What are some of the typical topics that appear to be off limits when it comes to discussing S3 storage solutions? And what are some of the deep questions you should really ask to surface some of those things that you need to know? So we'll end at the presentation with a Q&A, and at that point we'll close off. So Eric, I'm going to go ahead and hand this off to you.
Great, thanks, John. So let me jump in here with what is S3. Well, in the simplest, it is a protocol from Amazon Web Services for accessing object storage. It does not, as you noticed, describe a particular storage product behind the scenes. It doesn't describe anything about the management of a product. What do you as an admin have to do? What do you do when something happens, when something fails? What do you do when you need to add more of it? What do you need to do when users ask you for more space or for some kind of feature? S3 is really just about how applications use the HTTP protocol to talk with a storage system. And so it doesn't really give you much of more than say that it's NFS. Well, NFS doesn't describe anything behind the scenes. So the AWS S3 protocol is a way to access object storage, as I said. It's also part of the overall Amazon cloud and the Amazon services. So there are aspects of the S3 protocol that relate to AWS the service and other aspects that relate to getting at your object storage within a system. What's important to know about S3 is that it is a moving target. People say it's a standard or that it's a spec, but it's actually not either of those. It's whatever the latest API web page on Amazon site says it is today. So that means that people who are implementing the S3 protocol are constantly keeping track of the changes and evaluating which parts of those relate to access to object storage and which parts of those relate to AWS, the service. So, for example, we've had in the last couple of years big change between V2 and V4 signatures. There's even a variation on the V4 signature where you can do V4 without body signing on your requests. We've also had a recent change in how bucket listings are done. There's a change from the original, version 1, if you will, protocol to the version 2 bucket listings. So you need somebody who is keeping up with the S3 protocol. There are some, I kind of break them down. I have another webinar that goes into a lot more detail on this one, but you have your basic create, read, update, delete list or CRUDL actions for reading and writing objects into the system, and you'll have your basic object access control lists, which is where you put permissioning information on specific objects themselves. And then you have features of the S3 protocol that are really differentiating between a storage vendor that has implemented, just the basic CRUDL kind of operations versus the vendor who's really thought about this and gone farther and giving you stuff that you as an application developer or someone who is using applications that have gone farther can really make a difference in terms of how you manage your storage in the system. And that would be things such as the bucket access control policies. Again, I will refer you back to a webinar I did that goes into a lot more detail about that and how we actually stack those in terms of not just bucket access control policies, but how we go into a domain or tenant or even global management and stack those together. Another differentiating feature is the implementation of object versioning. Whereas, you write an object, and then you change it again, and maybe delete it. Do you have that history of the changes that went on with that object? Can you roll back and revert to those? And then the last one that I'm calling a differentiating feature here is multi-part upload. And it's not uncommon for people to implement the multi-part upload. It's not that difficult if you know the S3 protocol to do it. That's where you basically say that I am initiating the upload of an object, and the service says, yes, I'm ready. And you say, here's a part, here's a part, here's another part, here's another part, here's another part, and then you finish it with the, okay, I'm done. Please make an object from all those parts that I uploaded. And like I said, that's not overly complicated to implement that, but that's actually not interesting. What's really interesting is when you could have multiple independent writers all submitting pieces of an overall object, and you can actually gain speed by uploading them all in parallel. And that is actually the interesting part, especially when it comes to some high-performance computing kinds of applications where you're writing very large objects that may be distributed across a farm of servers. And so what you're doing is you're utilizing all the client network connections as well as all of the storage network connections in parallel to basically write an object faster than any one source could write it.
So Eric, it's fair to say here we're dealing with a protocol that is, as you said, a de facto standard. There's no official standard for S3 other than what Amazon publishes. We do have a quick question from the audience related to that. Do we happen to know how rapidly Amazon tends to cycle or update its S3 API?
Yeah, it happens when it happens. That's actually the best answer I can give you, because sometimes there are things that occur that occur in short order with each other that are important, such as the V4 signatures and then V4 without the body signing. And then there are times when you'll have months where there'll be no perceivable perceptible changes to the protocol that relate to object storage. You might have some changes that deal with, the rest of the Amazon service. So I can't really give you a pacing on that. The example of the V4 signatures was one where it was made for basically communicating over a highly untrusted communication channel, which would presumably be even where you didn't trust SSL, and to prevent replay attacks. Well, by forcing somebody to sign the body of an object, which is basically compute the SHA-256 hash of the body before you sent it to the service, essentially requires you to read an object that could be quite large, read an object twice, once when you compute the hash and once to send it to the service. And so that could be pretty restrictive in terms of performance there. And so very quickly, they then had this variation on the V4 where you could say that you weren't interested in that aspect of guarding on a replay, and you'd be doing a V4 signature without that body sign. So it's really kind of correcting an oversight that I think they had in the first go round with it.
Yeah. So it's fair to say that Amazon does this, ad hoc as needed, depending on their service needs. So it's kind of that's kind of one of the secrets that vendors may not, relate to you, is that they're not keeping up with a timed update on a spec.
That is correct.
They could be caught unawares by a change that Amazon makes, even when they're claiming that they're fully compatible. And it's really something that you should look into, but before you take that claim, at its face.
Yes. And the other thing to take is that what do they mean by S3 compatibility? Do they mean they've implemented the basic CRUDL operations, or do they mean they've gone farther with other parts of the protocol as it pertains to object storage? Or have they just given you a really basic, simple, works with some things implementation?
Yeah. Thanks, Eric.
It's a good question. Thank you. Okay, so what's missing? So you've got S3. So you've got the claim that we're S3, but what is missing from that? Well, as I said, it really is just a protocol. So that's great for the application, because the application doesn't care about doing anything else but speak an API to the system. But what about your storage administrators? What about your end users? And that last question is actually one that I'll ask about a lot of different products, because you've got a lot of content in the system. And while every vendor is giving you some kind of UI for your storage administrators to manage the system, that doesn't do a lot for your end users who maybe have a bunch of content in the system, and you'd like those users to be self-sufficient as much as possible, because I don't know about your organization, but we don't have a vast team of IT people that far exceeds our user population. So we've got a lot more users and a lot less IT people than you'd need to have your IT person do everything for you. So you really need to provide a user interface that has thought about the normal user who just has some content in the system. How do you let them do things like control policies on their buckets, to set protection levels, to search on content, see things that are in the system? Can you delegate out authority to do things like create your own storage spaces? We have other webinars where we do talk about our content management UI, and I encourage you to check those out. So what does it do beyond the protocol? How does it help administrators use the system, but how does it help end users do their own service work so that they don't have to use the storage administrators for everything? So I mentioned content searching there briefly. So remember our blogs and our webinars on the importance of object metadata. We feel very strongly about object metadata as a means to organize your content and finding your content and being able to get new value from content you put in the system beyond just the application that originally wrote something into the system. And you're thinking, well, that sounds great, but how do I really need metadata? Well, think of this. Amazon expects you to put tens of thousands or more objects into a bucket. Now, as a human, I am not going to be reading after about 100. So if I do a listing of that bucket and I see more than 100 things, I'm not going to stop. I'm not going to keep reading. You go to do a Google search. How many people make it to the second page of the Google search? Maybe a few. But how many people make it to the 10,000th page of that search? Exactly no one. So, I mean, that's the kind of scale we're talking about here. Is listing of a bucket is a very crude mechanism to manage content within a bucket. Our system is actually, again, back to other webinars we have here, our namespace lets you get very precise with your namespace. So you can give somebody an entire, what essentially looks like an S3 storage region with no overhead. So having buckets that says, my photos, and another bucket says my documents or my documents from this summer, that's not a big deal. But when you go to the expected use of S3, the protocol, you're really thinking in terms of putting tens of thousands of objects in a bucket. And so searching becomes extremely, extremely important at that point because listings don't do it.
So a quick question here, Eric, from the audience. Does the S3 protocol, as it's currently written, support any kind of searching or filtering mechanisms in regards to metadata?
No, it doesn't. That is not part of the S3. That Amazon, the service, gives you other tools by which you can write applications that make use of searching, but you'd basically have to write something into S3, write it into a database, and then implement some kind of query yourself in the application. And that's where we've kind of tied that together. And we provide you a ready-made metadata search mechanism within our storage system. We provide you access to that search mechanism in the end user interface. So the interface that you give to your users has that searching built into it. Our own HTTP protocol, which works in parallel with S3, implements searching within its actual API. So
I guess one of the questions you would want to ask is, great, you've provided me with an S3 endpoint to put data into, but if I need to go back and find things later, how do I do that?
Yeah, and actually, it's kind of humorous. I've seen a vendor that announced that they now have metadata searching, and you read the spec sheet for it, and it says that they basically stuff it into a NoSQL database, and that was their definition of search. It's basically, we stuck it in the database, you figure out how to use it. And it was humorous because I don't see that as an actual solution. That is, you jam something in a database and now I need to figure it out and hope that you don't change that. So that didn't seem very imaginative to me as an implementation.
Thank you.
Okay, so let me move on here. So what else is missing? Well, how about some advanced protection policies? How about mixing things like replication, whole object replication, as well as a variety of erasure coding choices, and mixing that all in the same cluster, or same domain, or same bucket, or even choosing them on a per object basis. And when I say mixing, I'm talking about whole object replicas living in the same storage space on all the same nodes as where you have erasure coding occurring. And whole object replicas are very good for performance because you can distribute the load around hardware within your cluster. And they end up being fairly efficient for smaller objects as well. Whereas erasure coding is good for efficient use of the physical raw storage when it comes to storing large objects. And we've got other webinars where we go into detail there. But being able to control that again through a user interface, being able to control policies related to replication and erasure coding, and what the erasure coding ratios are within your cluster, within domains, within buckets, or down to the object level. Again, giving you the granularity you need to manage your content. Whereas it's not just a one-size-fits-all of this is how I'm going to protect data that goes into this cluster, but rather it's I can have a default set of policies and then I can override them for specific data sets. So another thing that is often missing is geographic distribution. Sort of the basic level of geographic distribution would be just replicate my whole site. I've got 2 sites, replicate all the data in one site over to the other for our DR purposes. But I don't know about you all, but WAN bandwidth is at a premium for us. And so oftentimes you get into this choice of saying that, there's a subset of content that I've got in this system that really needs to be replicated. And maybe I've got subsets of content that need to be replicated to different places. So this set of content should be replicated to these 2 remote sites, whereas this set of content should be replicated to a different remote site. Maybe I have active deployments where I'm actually writing and reading data in multiple locations, and then I'm synchronizing them back together. So that's another thing that can be missing from other implementations that you could find quite important. Okay, so what are the taboo subjects here that John mentioned? What would we rather? This is a theoretical vendor saying we'd rather not discuss architecture. That's too dirty and boring. You don't want the details. We just be comfortable that we've implemented S3. Well, so let's go a little bit beyond that, because that's not a very good way to make a decision about where your most valuable corporate data is going to be kept. So let's talk about architecture here, and I'm going to do that by let's design our own S3 object storage system. So we're engineers. We like to design, but we're also practical. So let's use open source software as much as possible in this theoretical S3 storage that we're going to design here. So starting off, we need some servers that have disk drives, and those disk drives, we'll put a file system on them for storing our stuff. Linux is a good choice. Let's start with Linux, but should it be Red Hat, CentOS, Debian, Ubuntu? What should we use? What should we use there? In terms of file system, let's use ext4. That's the default. But I've actually always heard that XFS is really good for keeping up with small objects. It's efficient. I don't know why that is, but I've always read that. But also XFS is kind of old and nothing's been done on it since SGI contributed it a long time ago. Maybe we should use ButterFS. That's the new thing in Linux that it keeps feeling like it's about a year away from being done, even though some of the distributions actually have pulled it out now. So I don't know. Is ButterFS going to be the next thing, or was it the next thing that never happened? I don't know yet. So, but I do need to make a file. Should I use hardware RAID? Should I use software RAID? Should I use MD devices to keep things more reliable, or should I go for just raw and come up with some mechanism to synchronize data across those different systems? Okay, so we've got our storage layer, right? Mostly settled. We'll make some decisions later. Let's just go ahead and get started though. Next, we're going to need a database to keep track of where we put all the pieces. So we're going to scatter things all around these disk drives on these Linux servers. So we're going to need a database that's super fast. In memory would be good. That all these things can run. So they know where everybody has things. And I put Redis out here because that's I read something about that. So let's use Redis. We'll figure it out. Next, we need a place to keep metadata, such as directory listings, bucket listings, that kind of stuff. So let's bring in something like Cassandra. We need a persistent store there. That's I hear it's super fast because it can run some of the social media websites. It's eventually consistent, but I'm sure we won't have any troubles with that. So we'll put that there to keep track of metadata and other things related, higher level things related to the system. What else do we need here? We'll probably need a way to check to make sure everything is good, reprotect things if it's not. But actually, I'm sorry, I'm jumping ahead of myself here. We need some front-end servers because I forgot. We don't know how to get to. We've got these pieces scattered throughout all these Linux systems. We need some access node here to know how to translate the S3 request into something where it goes and finds it, goes and looks up what it needs to look up, and then gets the pieces and pulls them together and hands it back to the client. So, there's something that looks funny about that architecture drawing. We probably should add HA just so, we'll add 2 of those just in case one goes bad. That'll probably be enough. Well, as I said, I was worried about, how do you scan and make sure everything is where it should be. So we'll make this thing called a scanner that sort of ad hoc walks around all its disk drives and sees that things are okay and puts them back in place if they're not. So that'll just sort of troll across all the servers in the system. And if I get too many servers for it to keep up with, maybe I'll figure out a way to add multiple scanners to somehow go through them faster and in parallel. But for right now, we just got the one. We are going to need a way. Somebody's going to want to expand this system, unfortunately. So we're going to need a way to do that. They're not going to feel real happy about trying to do that themselves. So we need some kind of orchestrator that could handle adding hardware. So maybe we'll use something like Puppet or SaltStack, but SaltStack's kind of out now. Maybe Ansible somehow. So Puppet or Ansible, maybe those are decent choices. We could put something on there that is a way for people to add new hardware and have it sort of auto-magically deploy the right Linux and the right config and hook it up to all these pieces we put in there. Hopefully someone won't be removing hardware before we figure out how to handle that, because when the hardware starts getting old and you want to replace it with better hardware, you're going to have to take stuff out of there, but we're not going to address that yet. So that'll be a future thing. People are going to need to authenticate here. So let's get LDAP or some kind of Active Directory integration into there, so that we can keep track of multiple folks. But you know what? We've got a deadline to get this thing out the door. So let's just start with SQLite. Let's just do something quick and easy and put our users in SQLite. Maybe we won't have many users. Maybe we'll just have 2 classes of users, admins and regular users. We won't really bother much with access control. We'll just fix that later. Okay, well, that looks like a pretty complicated stack of stuff. And if we talk about that with end users, they might start to get, storage administrators, they might start to get a little scared of that. So we need to do something else that makes this look easy. I got it. Let's just call it an appliance. We'll call it an appliance, and it'll all be good. Okay, I'm sorry. That was a few minutes of tongue in cheek there.
Yeah, but fairly enough, there are many vendors that put out S3 solutions basically in that fashion. And to your point, Eric, it does help to look under the covers a little bit and get a feel for what exactly am I buying myself into when I'm getting ready to deploy an S3 endpoint to my end users, to my customers.
Yep. So my next question is, of you, the purchaser of the storage, is who's the lucky systems and software expert that you're going to designate as the one that's going to get to fix this in the middle of the night when everything goes wrong? And the first thing you could think is, don't worry, it's an appliance. And that's fine and great as long as all those components, all those open source components being developed by all kinds of independent groups, as long as they all stay in sync with each other and nobody loses a network connection or loses a transaction, then you'll be okay. Now, I've been in IT way too long to know that never occurs. That there is always, it chooses the worst time, but there's always something that can get out of sync. And so ask yourself, when you're looking at the architecture of a system, where can it get out of sync? And how does it recover from that? I say here, I'd ask you when it's going to get out of sync, but we all know the answer. It's going to happen when you're on vacation. It's going to happen over the holidays. It's going to happen in the middle of the night. You can be sure it's not going to happen at 10:30 in the morning after you've had your coffee and checked all your emails for the day, and you're now ready to fix a storage problem.
Yeah. So the ability to self-repair is key in that respect.
Yeah, and so that's something that we tout with our system, is this self-repair capability, is that it needs to be able to save itself without human intervention. Human intervention is for things such as, I need you to put some more server hardware in the rack because you're out of space. I don't know the software way around a hardware deployment until we get into Skynet in the future. So, you really need a way for the system to do everything it needs to do to protect itself and recover from outages. And you have to assume that everything is going to eventually fail. So there can't be any critical parts that you say, well, this one, we'll just put it on RAID, and then it won't fail. How many people have had a RAID mirror where it wrote the wrong thing to disk and it faithfully copied that to both sides of the mirror? Okay, so after you've asked yourself, where can the system get out of sync, also ask yourself, where is the metadata? And you might be saying, that feature you were describing of using metadata for searching is good and all, but we don't quite use that yet. And my question would be, are you sure? Because how do you handle listing requests? Those are typically part of the metadata related to objects. And so if you have a database that doesn't know what's supposed to go into a particular bucket, you've got a metadata problem. Not only that, you have a problem where your storage applications are going to be asking for the contents of the bucket, and the system is going to tell you, I don't know, or it's empty. So you probably do use metadata even if you're thinking that, well, we're not making use of the searching capabilities. And the other thing is, how does your system know where all these fragments are scattered about? One of the reasons of putting a bunch of distributed servers here with a bunch of disk drives in them is so that you can spread the bits all across the disk drive for protection purposes. Well, there has to be a database in there that knows how to put those back together. There has to be I say database, there has to be a mechanism in there that knows how to put them back together. I will actually tell you, it does not have to be a database. You can design the system so that it can be shared knowledge that is not database related in the system. So, who is the lucky expert in your company who's going to get to put this back together when something goes wrong? Okay, so that was kind of a tongue-in-cheek journey of how would we design the system if we were naively to forge ahead on this project. But ideally, how would you actually do it if you're going to do this the way that you'd like it to work? Well, you'd start with some kind of purpose-built clustering. And the reason I say that is because you need to be able to handle things like adding and removing hardware, removing just as important as adding. Adding and removing hardware should be looked at as normal tasks for the system. It should not be looked at as a forklift upgrade that you do once every 5, 7, however many years until you just get rid of the thing. It should be looked at as something that you do routinely, say every 3 years when pieces of storage become too, of the hardware become too, are not dense enough, too inefficient. You should have an easy way of telling the system to automatically flush that piece, get it out of there, and add in a new piece that is more storage dense, more efficient in terms of power or money. So purpose-built clustering that does things like just discovers that a new piece of hardware has come into existence and do whatever it needs to do to bring it into the system and start immediately using it. And when I say immediately using it, I'm talking about built-in load leveling here, where in real time it can start sending to a new node that has joined the system or a new disk drive that has joined the system. It can start sending user load there. It can also, over time in the background, also do load leveling to new hardware that has come into the system. You'd also want to have a purpose-built storage format. I was kind of making fun of file systems. File systems are very good at what they're designed for. They're very good at organizing storage blocks or storage, bits of storage into what is usually a B-tree data structure. But it's an allocation scheme of saying that I'm going to receive files. I'm going to receive requests to write files. I don't know how big they're going to be. They could grow over time. So growing over time means that it may have been a linked list of blocks, that 100 blocks to start out with, but then I add 20 more blocks onto it. Think about a log file where you're constantly appending to it. So, file systems were designed with this use case in mind, and they are very good at that. But what they're not as efficient with is they're not as efficient when you're trying to do object storage. And the characteristics of object storage is more about an immutable thing that is written down to disk and it persists and stays there until such time that it is obsolete and no longer useful, at which point the storage is released. And so you're allocating storage very differently when you're storing, when you're using object storage. And so if you use a file system, we have some blogs, and I think we talk, this might actually be the part of an upcoming webinar, is that if you use a file system, you're going to waste, easily, you're going to spend 5% off the top to format the file system to begin with. But then you're going to get this concept that you really need to run with the reserve from anywhere from 15 to 20%. You need to leave free so that you can let the file system efficiently manage this block allocation, deallocation process. If you purpose build a storage format, knowing that you're going to be doing object storage, you could do things like use 95% of the raw disk as actual storage space. And so, yeah, you have this 5% formatting overhead, if you will, but then after that, you're not constrained to some, performance reserve of 15 or 20% like you'd get with a file system. And so that's where using a file system can really be a kind of an Achilles heel in a lot of these, object storage implementations. Yeah, John, go ahead.
Just to elaborate on your point, what a lot of people forget when they're evaluating these various object storage solutions in the field and S3 implementations that are layered on top of them, is that you're trying to escape what we call, and we've mentioned this in a past webinar, Eric, the tyranny of the file system. Well, how can an underlying file system present so many issues to an object storage solution? There are many ways. There's the inefficiency that you talk about just now. There's inode pressure. People forget that one of the reasons that they wanted to go to a RESTful API storage solution to begin with is they're trying to escape simple things like inode pressure. They have a large number of small objects, for example, and sure, they have a lot of space, but they don't have enough inodes to track everything. It's particularly funny to see some of these vendors use extended 4 as the underlying file system for their object storage solutions, which has a 32-bit inode space. You're only talking about a few billion objects, then yeah, you're filled up your solution.
You're having to think about things in advance. You're having to know things in advance about how your storage is going to be used and how it's going to evolve over an unforeseen period of time. Yes. What you need to do is remove yourself from that and have the actual storage system itself do the thing you would actually want it to do, which is don't bother you with details, just be very efficient at what you do. So the other thing is that you would want to have a mix of heterogeneous hardware. And you're thinking, well, I'm just going to buy everything. I'm going to buy all the same stuff when I do. And that is true. When you do your initial deployment, you will probably buy all of the same servers and all of the same disk drives. But disk drives, like light bulbs, fail. And so, that incandescent bulb, you're no longer deploying those. You're deploying LED bulbs now. You had CFLs, a couple of years ago. So as disk drives fail, you're going to want to replace those failed drives with whatever the current, most bang for your dollar model is. And so if that means that you were doing 2 terabyte drives a couple of years ago, you're going to be buying 8 terabyte drives today. You're going to be buying larger drives than that tomorrow. And you're going to want to put them into servers that have the smaller drives as well as these newer, bigger drives. And you want the hardware, you want the system to just manage that difference. You don't want the system to tell you something really stupid like set up a RAID group with 2 terabyte drives. And so, yeah, you can add a new 8 gig drive, but we're just going to use 2 terabytes of it. We're just going to use 2 terabytes of it because we need the RAID group to have all the same stuff. Mm. So that's the kind of thing that you would not want the system to do. You would want the system to be able to manage the load across differing sizes of disk drives. Next year, when you need to expand and add more space, you're not going to buy the same, what would now be old hardware. You're going to buy new hardware that has different CPU capabilities, different network drivers, different disk drive sizes, and different storage densities. And so you want the system to auto adjust and use that hardware in the best way they can use that new hardware and load level across all of that across that space without asking the horrific question of asking the human how you balance load with new hardware. That is I go crazy that ask you to come up with some sort of balancing metric to say, how much better is this new system I've got? So how much load, which fraction more load should I send to it? And that is not a question a human can answer. You really need the system evaluating that on a real-time basis. The other thing you need is a single source of truth. I dropped in 2 different databases into that theoretical design there, where everything on each of those database sets is critical, where nobody else knows the information that was, if you lose one of those layers, it gets out of sync or corrupts itself. How do you rebuild it? There may not be a really good way to rebuild that thing. And so what I mean by single source of truth is you really need the object system itself to basically be the place where everything else is derived from. So we do use a NoSQL database in our system for augmenting our metadata. But one of the things you'll see in our design is that database can be rebuilt from scratch. I mean, you can burn it down and redeploy it, and you can recreate it as an automatic process from our storage system. So you don't want to have critical information that exists in multiple different systems throughout your architecture, because someday something will happen and somebody will get out of sync, and the unlucky administrator is going to be the one that has to participate if not be the person who figures that out.
And I think that's a key point there, Eric. Just to answer one of the questions from the audience real quick, it's more of an observation that, it sounds like this is an ideal solution to avoid single points of failure. And I would say, yes, that is a fair assessment, but it goes further than just single points of failure, as Eric mentions. It goes to this concept of a single source of truth. Where does your metadata live? Who is the final authority for whether or not that metadata is up to date, accurate, or not? And when it comes to that, not all solutions that are available are equal. Speaking as to how we do it, our metadata is actually stored with and protected in the same fashion as the data. The objects are a coupling of metadata and data together, and they're protected together as a whole object. And not everybody does it that way. And it's something you need to watch out for, because as Eric mentions, if your metadata database system somehow gets out of whack or becomes unavailable, how quickly can you repair it? How quickly can you true things up to reflect reality in the system, and so on? It's very important when you have real data in the system.
Yeah, and so was the reparation of that data part of a design decision, and the process was thought about by the storage vendor, or is it it'll probably never happen and we think we know how we tell you to do it kind of situation? You don't want to.
Or they just tell you they just tell you to be religious in backing up your metadata database, and they move on. But realistically, that's not the best answer.
That's right. So also, you would ideally want to have some kind of metadata searching engine. You'd want it designed for ad hoc searching, because part of the importance of metadata is that you can derive value from it today, but in the future you may derive value from data you stored in one application by being able to correlate it together with data from other applications and use it in ways that you hadn't thought of. And so there's this idea that you can sort of decide in advance how you're going to use searching is kind of a fallacy, because you do not know how you're going to use searching a year, 2 years, 3 years from now. It's going to change and evolve. And so you need a way to do ad hoc searching where basically you're not bound by a schema, you're not bound by any kind of initially decided constraints. You'd like you'd like your search engine to have flexible field typecasting. So, string values are sort of a good starting point, but what about numeric comparisons? Is this greater than something else? What about geographical coordinates? Does it fall within this area, this latitude, longitude area? Those are also important kinds of things and possibilities you could have from metadata searching. And as we discussed, you want it to be able to be constructed completely from the object system. So you don't want what's the contents of a particular bucket to be the sole source of authority, be some external database that you sure do hope that it stays in synchronization, because if it gets out, you won't know where things go. So you really want the object system to be the place where that is the single source of truth for that. Okay, so I'm running along here. Let me keep forging ahead here. What else would you want in an ideally designed system? You would want your content, their gateways into the system. You'd want those to be stateless, and you'd want them to be horizontally scalable. By stateless, I mean I could, at any one time, there is no special configuration on any of those front-end gateways. I could just decommission one, and there wouldn't be anything for me to worry about saving off of it. Or it could have a complete total failure, and there was never any data that was in flight, or any data that had been acknowledged to a client without having been put into the back-end storage system. You'd want those front-end gateways to really just be a bump on the wire, is the way I put it. That you're pushing bandwidth in through the front side, and it comes out the back side with very little with very little overhead on the way through itself. So it's almost like a perfect reverse proxy. That content gateways, those would be the place where you have authentication, authorization, auditing, and accounting. So accounting things like quotas. You'd want it to be the place of authority for all of those actions. That includes tie into things like LDAP, Linux PAM, Active Directory, all these external identity management systems. If you do not want to be in a place where the identity management system for the storage is a separate database that exists inside the storage system, because the first thing you're going to do is have it know about your users that are already in LDAP or already in Active Directory, and make access control policies based upon those corporate users, not a different set of users that are in the storage system. I mentioned that you really want to have self-service for your end users. I was talking about that with the user interface. Have you thought about ways that your users can do for themselves without having to involve the storage or IT people in everything like, I want some more storage space. Okay, I'd like to provision a different domain in which I'm going to store things. What you really want is for storage administrators to set up the rules ahead of time for what someone's allowed to do, quotas for what they're allowed to take from the system, and have the system be the one that monitors that, your compliance with those. And then ideally, you'd also want your content gateways to have REST APIs for everything that you can do through the UI, because the UI is great for end users, but I guarantee you some portion of those end users are going to one day ask you, can I write a script that does blah, that checks my quota? Can I write a script that checks the bandwidth on a bucket in the system? Can I write a script that goes through and profiles how I've used the storage over time? Well, you want a system that says yes. Yes, you can. There's a REST API. Everything you can see in the UI can also be done through REST APIs and automated.
Yeah. That last bullet people miss a lot when they're evaluating these various solutions, Eric. One of the huge tasks that an admin has to face is the combination of batch provisioning and batch deprovisioning.
Yep.
And if all you hand them is a UI and you don't hand them an API to perform those operations, that's a lot of clicking for the poor admin that's given that task. But if they have an API where they can automate that and batch it up and script it, that's a big win for the solution.
Yeah, years ago, I'm probably giving away a secret here. Years ago, I used to ask an interview question of Unix admins and say, how do you add a user to the system? And I'd get an answer. I'd go through this, I'd do this command line. Then ask, how would you add 100 users to the system? And then it gets into now I'm thinking about, okay, I'm going to have to write some script for this. I'm going to have to take some input from somewhere. I'm going to do something. So you're really thinking about automated actions when you're talking about more than one thing at a time. And so that's where these REST APIs are very useful. Most users won't get there, but some will. And if your system doesn't have a provision for it, you're just sunk from the beginning. Okay. So the key takeaway from this talk is that architecture really does matter, and it's not a taboo subject. It really needs to be discussed. And you don't have to understand all the bits of the architecture that is discussed, but something that's useful to consider is, after hearing explanation of what are the pieces to the system, what do they do and how do they work together, is, can you, in general terms, could you take away from that and explain the general theory of operation of your S3 storage product to somebody else? Do you essentially have a grasp for how it load balances, what the characteristics are, or how it actually protects your data when drives fail? I don't say if, drives fail. So when drives fail, when servers fail, how does it protect your data? Can you answer that after hearing about the architecture? And one of the things I'll point out is that when we say when Koringo says simple about our storage system, that's actually a word I hear a lot of other vendors say simple now as well. I don't know what they mean by simple. I really don't. I'll tell you what we mean by simple, and that is that you can essentially understand what our system does, and you could explain this theory of operation. And I would pose to you that if you can't kind of grasp how the system is going to recover in the worst kind of cases, if it's very complicated and it's kind of just magic about how it works, then it probably means the system's not going to do that. You know, when the chips are down and things are bad, it's probably going to do something wrong. And so if the explanation's not simple, then the implementation is probably not going to behave in a way that is simple for you to deal with in the end. So you know, the architecture may kind of seem like an academic discussion up front, but when your data is all in the system, it's not going to be so academic any longer. And things like the disk storage efficiency, you know, are you able to use 95% of the raw storage for your storage? That kind of efficiency is not so academic when you start getting up into the petabyte range, because now a 15 or 20% storage reserve could be a significant chunk of raw disk drive storage in the system. And so I'm going to leave you with this. There's actually a lot more discussion that we can have here about our architecture, and I didn't have time in an hour to cover all of it. We have other webinars. We have future webinars as well planned for this, but we'd also like to talk to you in person if you'd entertain us. So we do love to talk about this stuff, and we do have a story to tell, which we believe is simple, that you will understand at the end of it how our system works together. So ask us the hard questions, and ask the hard questions of our competitors too, because this "don't worry about it" as an appliance, it magically happens. That's all great until it doesn't, and then it's your problem in the middle of the night in terms of figuring out how to get your data back and solve it.
Very good. Thank you, Eric.
That's all I've got. That's all I got for you. I think I got 2 minutes to spare. Maybe only one. I mean,
no problem. Thank you very much, Eric. And thank you, everyone, for joining us today. To keep up with Koringo, follow us on Twitter, LinkedIn, or Facebook. If you have additional questions or would like to schedule a custom demo, please email us at info@koringo.com. I'd also like to invite you to join me and system integrator, Avi Felsenstein, for the June Tech Tuesday on June 11th, as we discuss monitoring Swarm using the Prometheus exporter and Grafana. Thanks very much, everyone, and we hope you enjoy your day.